Hello students, this video is a review of that sample final that I sent out to you. I hope to talk about all the different topics that you might see on this final. I also want to review some of the commonly misconceived or common misconceptions here in statistics. Let's take a look at the first question. It gives us some raw data here, 30 bags of laundry, their weights, and it asks us to complete a frequency distribution table for this data. So in this table, there are a couple of different columns that you need to identify. The first column here is weight in pounds. It's asking us to use 8 classes of width 3. That means all of the classes have to have 3 weights within them. So from all the 11 weights, all the 12 weights, and all the 13 weights, all the way up to 13.9 are here, 14, 15, 16, 17, 18, 19, etc. One easy way to do width of 3 for classes is to start with a fixed number, let's say 11, and then add 3 to it. That's going to be the lower bound of the next class. Add 3, lower bound of the next class, etc. And then the previous number is just going to be up until 14 or 13.9 in this case, because we don't have any decimals that are more than one value. All right, the next column is tallies. We're just counting the number. You can see the check marks here. We're counting the number of data values that fall within these classes. So there's one data value that falls within 11 to 13.9, and that's 12.1. 15.2 is one of the ones that falls within 14 to 16.9. There's 4 of those in total, and so on and so forth. The frequencies are just turning the tallies into numbers. The relative frequency is dividing the frequency that we found by the total, and in this case there are 30 total bags in our sample, so I'm dividing by 30 every single time. Notice that all of these had to be, or almost all of these had to be rounded to the nearest hundredth. Anytime it tells us to round to a certain value, we're going to do that. Cumulative frequency is adding the row to the previous row. So for example, I know that this cumulative frequency is 1 because the frequency over here is 1 and there's no rows above it. However, this cumulative frequency is 5 because this frequency here is 4 and I'm adding it to all of the frequencies above it. This frequency here is 26 because I'm adding 3 to 11 to 7 to 4 to 1. Cumulative sounds like accumulate, and cumulative should be gathering together all of the values at that row and all the rows before it. Notice that this value here should always be the total because this is the last row. 30 is equal to all of these other frequencies added together. We're asked to use the frequency table next to compute the sample mean. If I'm looking at this sample mean, I know that it's equal to the sum of all of the values times all of their frequencies divided by the total frequency. In other words, take all of the values that we've observed, multiply by how many times we observed them, and then add them all together. Then divide that by the total number of objects or items that were observed. So it should be fairly straightforward to figure this one out. The only hiccup here was it says I'm supposed to identify each value. Here we're actually using midpoints because these classes are not one specific value. I can't just choose 11 or 13.9 or 14. I have to choose the midpoint of the classes because what I'm saying is this one value is represented in this class, and this class's middle point is 12.5. That's a value that's pretty representative of the class as a whole. Adding those all together and multiplying those all together respectively is here, dividing it by 30, which is the total frequency, I get 21.3. Now, when I find the sample mean of 21.3 does represent the fact that, on average, all of these bags weigh 21.3 pounds. That should make sense to you because any other time we find a sample mean, it's the average value of the data set. Moving on to question number 2. In this question, it gave us a computer output that talked about constant coefficients, caffeine coefficients, R values, R squared values. You were not always going to use all of these values. As a matter of fact, in MAT120, in elementary stat, we're only talking about the correlation coefficient, which is R, the constant coefficient, which is the y-intercept. You can think of the constant coefficient as the constant in the y equals mx plus b, or the constant in as terms of the y-intercept. The caffeine coefficient is the number that we're multiplying by the amount of caffeine. Think about that as the slope. It asks us to write it in the form a plus bx. Since it says that specifically, I'm going to follow its directions. A then was going to be the constant coefficient. It doesn't have an x next to it, so that's 2.544. And then b is the slope here. B is the caffeine coefficient, the number we're multiplying by the amount of caffeine, which is x. So 2.544 plus 0.164x. Notice we're not using this SE coefficient. This is for the purview of another class. Same thing with R squared and R squared adjusted. We're not using that in this class. Using this regression equation, if a person were to ingest 50 milligrams of milligrams, I should say, of caffeine, that's x equals 50, how long would you expect the person to study for? Just plug it in, substitute, right? And we're solving for y, which is the amount of hours. That's an easy one to do. And similarly, section C is easy because we're substituting, except this time we're substituting for y. Because it tells us study for 8 hours. That means, looking back here, number of hours spent studying is y. I substitute in for y. Easy peasy. For letter D, it says an increase in caffeine intake by 3 milligrams would lead to what change? Well, keep in mind, the constant, this 2.544, isn't going to change if I ingest 3 milligrams or 300 or 3,000 milligrams of caffeine. The constant doesn't change. The thing that changes is going to be based on the slope. 0.164 times x means for every increase in x by 1, I'm increasing y by 0.164. So I'm basically saying 0.164 times 3 times this x value, because we know the caffeine is x, is going to be 0.492. So the constant's not, the constant's not going to change, but the slope is going to increase 0.164 3 times. That's 0.492. Not bad. For question 3, this is an example of a probability table, two-way table you could call it. This is all of the folks that either survived or died on the Titanic when it sank in 1912, over 100 years ago. Wow. There were people in first class, second class, third class. There were also people in the crew, and the total number of people on that ship was 2,201. The missing blanks in the table, it's just a subtraction problem. For example, I have this number, and I don't have this number, but I have this number. So I can say, well, 118 plus something is equal to 285. Or I could just subtract backwards. 285 minus 118 is 167. I'm going to let you figure this part out on your own because this is just adding and subtracting, and that's not my job. If a passenger is chosen at random, I can choose from 2,201 passengers. Yes, I'm counting the crew's passengers. Find the probability that the passenger was in the crew. Well, there's 885 total folks in the crew, so 885 divided by 2,201. The probability of crew is 885 over 2201. You don't have to simplify this at all, but I tried this in the calculator. I did math enter for this, and it gave me 885 over 2201, so you don't have to simplify, just leave it as is. If a passenger is chosen at random, same thing, we're choosing from the 2,201. The probability that they were in first class and they survived. Okay, well, the people that were in first class, that's all of these people. The people that survived, that's all of these people. Looks like we're only looking for these people, the folks that were in first class and survived. So that is 203 divided by 2,201. In this case, we're not looking at and, we're looking at or, which means either. So there's a couple of different ways to do that. You do need to know this formula or know how to use this formula, but with the two-way table, it's a little bit easier. Died or in third class, okay? These are all the folks that happened to die. Let me highlight those. Here we go. These are all the folks that died. And these are all the folks that were in, what are we talking about, first class? No, we're talking about third class. So here's all the folks that were in third class. Notice that there's an overlap here. So I'm going to add together all of these numbers that you see that are highlighted, and then I'm going to subtract out 528 because I counted that number twice. You can see that's basically what the formula asks us to do anyway. Add all the numbers together and subtract out the guys that were counted twice. Now this one is a little bit different. It says if first class passenger was chosen at random, you can see that first class passengers, there's only 325 of them total. Find the probability that, where are we at here? Find the probability that that passenger survived. So there's 203 survivors in first class. So 203 is definitely our numerator. The denominator is all the people in first class. That's 325. This is an example of a given probability, conditional probability, because there is a given conditional, they have to be first class passengers. If the passenger was chosen at random, find the probability that they survived given that they were in the crew. Remember, given is a conditional probability. It means the denominator is going to be a little bit different. In this case, given that they were in the crew, there's 885 people that were in the crew, so 885 is our denominator. We're looking for the probability that that passenger survived, so I'm looking at only the crew, the survivors of the crew. That would be 212. So there's my 212. Also, please know how to use these formulas because, hint, hint, you might have to use them on the final. For question 4, this is a probability distribution, and it's easy for you to figure out if you just read the problem carefully. It says we're looking at, stand by here, it says we're looking at a carnival game where people pick cards from a deck. just the not just the face cards, rather, just the number cards from 2 through 10. 2, 3, 4, 5, 6, 7, 8, 9, 10. The other cards are aces, kings, queens, jacks, etc. So we're only looking at the numerical cards. If you pick an even card, you win $4. If you pick an odd card, you lose $6. Seems like a pretty good game, right? Because there's more even numbers than odd numbers. There's 1, 2, 3, 4, 5 even numbers, whereas there were only 1, 2, 3, 4 odd numbers. And all these odd numbers, you're losing $6. All these even numbers, you're winning $4. And the probability of picking any of these cards is 1 out of 9. How did I get that? 1, 2, 3, 4, 5, 6, 7, 8, 9. There's 9 cards here. So the probability of picking a 2 is 1 out of 9, etc. Remember that when we're looking for expected value is probability times payout. It's, in other words, all of the different values of the random variable times the probability of that value. So 4 times 1/9, because I'm looking at 4 here, times 1/9 here, and then I'm adding -6 times 1/9, -6 times 1/9, and then I do the same exact thing for every single one. I'm adding them all together. Let's just check to make sure we did it right. This is the outcome for 2, this is for 3, 4, 5, 6, 7, 8, 9, and 10. Because 10 is it's an even number, so I get $4, and it's a 1 out of 9 chance of getting that. Putting that all into the calculator, I get -0.04 repeating. It asks us to round to the nearest hundredth, which makes sense because we're talking about dollars and cents. And if you didn't round it there, it wouldn't make sense. All right, -0.44 is our expected value. After playing this game many times, the average game's result is a loss of 44 cents. Notice, if I play this game one time, it's impossible for me to win or lose 44 cents. If I play it one time, I'm either going to gain $4 or lose $6. However, an average game, after playing it many times, the average payout is going to be -44 cents. In the long run, you lose money, which means if this game is worthwhile to play, I would be gaining money. It's not worthwhile to play because I'm losing money. The expected value is negative. Remember, E parentheses X is expected value. If I play this game 57 times, wow, that's a lot of times. How much money do you expect to win or lose? I'm just going to multiply the average payout by 57. So that's -25.08. $25.08 we're going to lose. Remember to say lose here, because if you don't, you lose. Question number 5 is talking about a Rangers fan. I don't know why anyone would be a Rangers fan, but let's keep going on that. We're trying to figure out whether she'll see a fight when she goes to watch a hockey game. According to hockeyfights.com, which is a real website that I actually did visit, 1,271 games, 238 fights. The probability then is approximately 18.7% of seeing a fight at a game. This is ignoring the idea that some games have multiple fights. We're trying to get an accepted value for the population parameter for proportion of games. Is this a binomial experiment? Yes, because a binomial experiment needs 4 things. It needs a fixed number of trials. I'm not going to say, I'm going to attend games until I see 4 fights. Nope, fixed number of trials. I'm going to do 9 games and count the number of fights. Fixed probability of success, 18.7%, just talked about that. That number is fixed, it's not going to change. Independent trials, that means that one game's fights don't affect another, which is probably true. And only 2 outcomes. Either you see a fight or you don't see a fight. It's not like, oh, well, there was kind of a fight. The fights are measured by whether the player gets a technical penalty or not. If the Rangers fan attends 9 games, what's the probability that 4 of them will have fights? Well, this is binomial probability, so I'm going to use the binomial probability formula here. This first number is the number of trials. This second number is the number of successes. I don't know if successes could be counted as a fight because nobody wins in a fight. But anyway, this is the probability of a success. That's 0.187. This is the number of successes to the 4th power. This is the probability of failure. It's 1 minus 0.187. And this is the number of failures that we want, because 9 minus 4 is 5. Easy to figure out, and you're able to figure this out on your calculator as well. 0.547 is your correct answer. 5.47% chance that 4 of the games will have fights. With this next problem, we're talking about not a probability density function, but a probability, a cumulative function. So more than 6 of them will have fights. So it could be 7 games, could be 8 games, or could be 9 games with fights. So what we're going to be doing is using one of the calculator tools. The calculator function is called Binomial Cdf or Binom Cdf. 9 is the number of trials. 0.187 is the number is the percent of success. and 6 is the number below which we're trying to calculate. Keep in mind that these are the same arguments that we used in this formula, except the calculator is able to put the numbers where it's supposed to be by itself. I'm using 1 minus because probability using binomial CDF is only able to be used with numbers that are below. Like if this said less than 6 of them, I would be able to use binomial CDF very easily. Since it says more than 6 of them, I need to use this 1 minus. This was in the slideshow. So 1 minus 0.09998 is 0.0002. It's a very, very small percent chance that more than 6 games will have fights. So she's probably good to go. The mean and standard deviation, this is a very easy question to answer because you have your notes with you. You're going to be able to use your notes for the final. This mean is equal to n, the number of trials, times p, the probability of success. Easy to figure out, and we're supposed to round to the nearest hundredth, so only 2 decimal places. The standard deviation, this is the symbol sigma, that's equal to n, the number of trials, p, the probability of success, 1 minus p, the probability of failure, square rooted. That's 1.17. That's all she wrote. Question number 6, the ages of the top 10 male finishers of the Boston Marathon in 2019 are listed below. We got all these finishers. Looks like they're all in their 20s or 30s. This guy's maybe a little bit old. This guy's maybe a little bit young. Maybe we'll get to that later. Find the 5-number summary of these data. You don't have to show a whole bunch of work for this. You just say, I went to stat calc, one of our stats. Hopefully first you went into stat edit and put the numbers in because otherwise the calculator doesn't know what you're talking about. Anyway, the 5-number summary is all of these numbers. We need the minimum, quartile 1, the median, quartile 3, and the maximum. Those 5 numbers describe the data. We're next supposed to conduct a test for outliers. That's going to be your outlier fence test. The outlier fence test is another thing that is in the slideshow. It's just a formula that you need to remember. These are the fences. The lower fence means if it's below this fence, it's an outlier. The upper fence means if it's above this fence, it's an outlier. The lower fence in this case is 25.5, and the upper fence is 37.5. Oh, well, check this out. It says there are 2 outliers. 25 is below 25.5, so it is an outlier. See what I talked about before? I said that 25 seemed a little low. And 38 is above the upper fence. Oh, 37.5, 38. I told you that 38 seemed a bit high. I mean, I knew it already. I'm just playing around with you. Draw a box plot. Easy to draw a box plot. However, there's one thing that you need to keep in mind. It says to indicate outliers, if any. So before you start drawing the lines, keep in mind that 25 and 38 are both outliers. So here's what we're going to do. We're going to put asterisks at 25, asterisks at 38, because those are outliers. So we're still able to label quartile 1, the median, and quartile 3. These numbers, though, are a little bit different. Where am I going to get 29 and 34 from? Look at the data. The smallest number is 25, but we identified 25 as an outlier. No good. Can't use it. So I'm going to use the next smallest number as my lower bound of my box and whisker diagram. That would, of course, be, where am I at here? It's not 25. It would have to be 29. And a likelihood of, similarly, 38, I can't use it because it's an outlier. So I'm going to use the next biggest number, that's 34. Check that out. Beautiful box and whisker. Question number 7. A large suburban school district with 2,450 students, that's a lot. That's like the high school that I went to high school at. The guidance counselors say the GPAs are normally distributed, mean of 2.3, standard deviation of 0.6. This is a calculator question. Oh, thank God for calculator questions. We're looking for above a 3.8 here. So above a 3.8 means I'm looking for, if I'm looking at the normal distribution here, here's my mean, which is about 2.3. I'm looking for the likelihood that it's above a 3.8. So 3.8 is going to be here. It's going to be very large. And I'm going to be shading in the area that's above the curve. In other words, I'm looking for all the values from 3.8 up towards positive infinity, which is 10 to the 99th power. The normal CDF goes lower bound, upper bound. That's right, the mean, the standard deviation. So 0.006 to et cetera, et cetera, et cetera. This is the percentage of students that is above 3.8. So that's just the percentage, keep in mind, right? We're not talking about percentages here. It's asking for how many students. So I'm going to multiply that percentage by the number of students, 2,450. That's about 15 students. I think it was 15.06, but I'm not counting that 0.06 of a student because that's gruesome. A GPA below 1.0, same idea, except my normal distribution here Ooh, disgusting normal distribution. My normal distribution here isn't going to be based on 3.8. Now it's going to be based on 1.0, which is less than the mean, which is 2.3. I'm finding all the values that are below this value, or the area below this value. That means negative 10 to the 99th is my lower bound. My upper bound is 1. Here's my mean. Here's my standard deviation, just like before. 1.5% of students in danger of failing. Why am I leaving this in percent? Because it asks for a percent. Why did I change this to number of students? Because it asks about how many students. Read the question, RTQ, answer the question, ATQ. That would be a letter C. The principal says, I want to have a pizza party, but we're only looking at students at or above the 95th percentile. So let's check where the 95th percentile is. 95th percentile means we're looking at 95% of the data. So I'm looking at the normal curve and I'm saying, well, what value has 95% of the data below it? So 0.95 goes in the area place, 2.3 and 0.6. Stop me if you heard this one before. This is the mean and standard deviation. That's 3.286, etc. However, we can't use this number. We're supposed to round to the nearest hundredth because that's what we do with GPAs. So 3.29 is the cutoff. Other than that, you can't have pizza. Question number 8, we're talking about Beanie Babies, which are small stuffed animals. The distribution of weights of a certain type of Beanie Baby is approximately normal. That's important because then we can use our normal CDF. Mean of 8.7 ounces and standard deviation of 0.5 ounces. Now we're looking for the probability that one randomly selected Beanie Baby will have a weight of less than 8.3 ounces. It's the same as the question before. 8.3 is the value that we're looking at. Negative 10 to the 99th is our lower bound. 8.7, 0.5 are our mean and standard deviation respectively. I got 0.2119 as my probability. I'm supposed to round to the nearest tenths, hundredths, thousandths, 10,000ths. For the next one, it asks the probability that a random sample of 30. Wow, this is a lot different than one Beanie Baby. Now we're talking about a sampling distribution. The mean of a sampling distribution is the same as the mean of the population, so that's fine. That 8.3 stays. Stand by. Found a typo. Okay, this should not be 8.3. This should be 8.7. So let's scribble this bad boy out. We're going to call this 8.7. 8.7, because that was the mean that we had before. Phew. Glad that's over. Now, the standard deviation of this sampling distribution is going to be the standard deviation of the population divided by the square root of the sample size. And we said the sample is 30. So we're going to do 0.5 divided by the square root of 30, which is 0.091, blah, 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 blah. Now we're going to do normal CDF using this number, or all of these numbers. Notice that all of the numbers are the same except for the standard deviation because I have a sample now. My sample is going to have a different standard deviation. Same mean, different standard deviation. I just put this in the calculator just like this. I don't bother with writing this nonsense into the calculator. I just put it in just like this, and it gives me the correct answer. Now notice, it's asking us to round to the nearest 10,000th, tenths, hundredths, thousandths, 10,000ths. The next number is also a 0, so I'm going to put 0.0000. I can also easily just write the big old goose egg, 0. That's a terrible 0. Sorry about that. The probability that a random sample of 30 Beanie Babies, I'm still using this idea of divided by the square root of 30. A weight of more than 9 ounces. Now I'm talking about 9 being the lower bound, positive 10 to the 99th being the upper bound, and all the other numbers being the same. This one you can round. Tenths, hundredths, thousandths, 10,000ths, that 0.0005. For letter D, it asks us to draw the sampling distribution. Just draw a normal curve. You know the middle is supposed to be 8.7, no big deal. We're supposed to use sample size 30, which means our standard deviation is that number that we calculated before. It asks us to round to the nearest hundredths, so 0.09 is the number that I'm rounding to. So from 8.7, I'm going to add 0.09, 1, 2, 3 times, and I'm going to subtract 0.09, 1, 2, 3 times. This first value is called the inflection point. It's what happens when you take the mean and subtract one standard deviation. This is the mean plus one standard deviation, and I'm doing it 2 more times to show all 3 of the standard deviation values. Moving on to question number 9. This one's about confidence intervals, and I'm confident that you are able to do these because we talked about them during the slideshow. There are 37 courses offered during the spring semester. The sample is approximately normally distributed, which is good because we are able to use our statistical methods that assume normality. It's got a mean of 102 and a standard deviation of 21. Incidentally, since we have 37 courses, that's more than 30, so we're able to assume that the sampling distribution is normal as well, but it's always nice to hear that. It's always nice to hear, oh no, it says the sample is approximately normally distributed. So that's important for our use of either Z or T, which I'll get to in a second. Mean is 102, that's X bar. Standard deviation of 21, that's S. So I want you to be careful here because there's two different things that you could do here, but one of them is more right than the other ones. This procedure, the Z procedure, is what happens when the confidence interval has a standard deviation that is known, a population standard deviation that is known. If that's the case, then I'm able to do these calculations and I get this and I get this confidence interval. However, in this question, it does not tell us what the standard deviation of the population is. It tells us the standard deviation of the sample. So technically, we're not really supposed to do this method. We're supposed to use this method, which is not the Z method, but the T method, which is very similar. It's also in your calculator right next to Z, but it does require you to tell the calculator the number which is called degrees of freedom. Degrees of freedom just means the number of items in your sample minus 1. So in this case, the degrees of freedom is 36. Regardless of that difference, you can see that there isn't that much of a difference. This is 95 to 109. This is 95.23 to 108.77. So not a huge difference. We're losing, what, 23 cents on either side. Is a difference. It is a statistical difference. However, if you did this procedure on the final, you would get some credit for that because you're using an assumption that that is not true, but all your other math should be good. And also, regardless of the result here, you are able to interpret it in the same way. We're 95% confident that the true mean textbook cost for the spring semester is between, here we're using the correct values, 95 and 109. Again, if you use these numbers, 95.23 and 108.77, you'd be close. So you'd lose a little bit of credit, but you'd be close. Last but not least, let's talk about the significance test. Remember that I talked about significance tests in that slideshow. The first thing we're going to do is try to write a pair of hypotheses for the situation. The null hypothesis always talks about a parameter. Here we're talking about mean length of bolts, right? The average length is the same as the mean length. So mean is mu. We're not going to use X bar because this is always going to be a population parameter, not a sample statistic. 6.1 is the accepted value. It says the bolts have to be 6.1 inches in length. That's the thing that we're accepting. And we're using less than here because she believes that the bolts are shorter than they're supposed to be. Shorter means less than. All right, same thing as before. In this situation, we don't know the standard deviation of the population. If you use this procedure, this Z procedure, you'd get negative 3.52. That is not very close. That is a very small Z value. Remember, it's like 3.52 standard deviations lower than the mean. It turns out that if you use this method, it's going to be the same T value, right? Because you're doing the same calculation here. The difference comes in when we do the normal CDF step. This is the last step to try to find our P value. The normal CDF step does require us to put in negative 10 to the 99th, that's a lower bound. The upper bound is going to be negative 3.52, and this is the mean and standard deviation of a normal curve, a Z curve. That gives us a p-value of an extremely low number. However, on the other hand, what we're supposed to do when we don't know the standard deviation of the population is use T. And T uses something that's a little bit very slightly different, same lower bound, same upper bound, but here's 53, and again that 53 is coming from degrees of freedom, which is 54 minus 1. I'm getting a p-value, and hopefully that you see this. This p-value is also extremely, extraordinarily small, 0.0004 versus 0.0002. Regardless of which procedure you use, either T-CDF or normal CDF, you are going to get a value that will lead to the same conclusion. Speaking of conclusions, let's write the conclusion. The p-value is less than alpha, which means 0.002158 is less than 0.05. Remember that alpha value is always going to be 0.05 unless it specifies otherwise. So if this p-value is less than this alpha value, we reject H null. Guess what? Both of these p-values are way super lower than 0.05. So regardless of which method that you used, either the slightly incorrect method or the totally correct method, you would still reject H null. We have sufficient evidence to believe that the bolts are shorter on average than 6.1 inches. How about that? All right, this was a video that reviewed the sample final from spring 2020. Good luck studying.